everybody. Hello. Welcome to a video on exercise number 9 of the handout of the Fourier Transform lesson. In this exercise 9 and also in the following one, we will do exercises that consist on following a signal through several paths and getting the shapes and the functions of how the signal get transformed going along the path. In this case, they give us this connection that you can see over here. They give us the signal xt at the input of the connection, which is this one. And also they give us more information that we will be seeing along the way. And they ask us to obtain the spectrum or the spectra of the signal at different positions of the path. For example, they ask us to get the spectrum over here, the spectrum over here, the spectrum over here, and finally the spectrum of over here. And then on part number B, they ask us to find the temporal, the time expression of the output. Okay, so the way to go through these exercises is go step by step, following the signal and applying, in each case, the operation that is indicated. Okay, so the first thing that we will do is transform the input signal x of t, and we will get the Fourier transform of x of t, which we will call x of omega. So x of omega is the Fourier transform of x of t, which is the Fourier transform of so x of t, which is given as data. So this is omega 1 divided by 2 pi sinh square of omega 1 divided by 2 pi t, as given here. So note please also this relationship between different variables that we will find along the way, which will be variable t1, variable tau, and variable omega. So these three variables, t1, tau, and omega, will be found, and we have to have this present. Okay, so we have the task here to Fourier transform sinh square. So to do that, remember that we did in an exercise, we calculated this Fourier transform. What is usual is to have in time a triangle signal, and this will get transformed in frequency in a sinh square. But here what we have is a sinh square in time, which we think or we can suspect that this will translate into triangle in frequency. And this is what we calculated in one of the exercises using the duality property. The result that we got at that time was this one. The Fourier transform of a sinh square of this form is 2 pi a triangle of omega divided by tau divided by 2. So a triangle in frequency of a half duration tau divided by 2 and amplitude 2 pi a, capital A, transforms in a sinh square, as you can see over here. And we use exactly this to transform our case, and you will see that the result is the triangle of amplitude unity 1 of omega divided by omega 1. So in other words, x1 of omega in frequency will be a signal like this. So remember that in the case of the triangle, we put here half the duration, so this will be omega 1, and the amplitude is 1. This is x of omega, the signal that we put at the input of our system. Okay, so now we are ready to go for the first one. Let's go and calculate x1 of t. Sorry, x1 of omega. So x1 of omega, as you can see, comes from the multiplication of x of t with a train of deltas. So in other words, x1 of t, it's equal to x of t times the train of deltas. We have seen also how to, in a previous exercise, the transformation of a train of deltas. So we are ready here to do the Fourier transform of this signal x1 of t and its x1 of omega, and the Fourier transform will be capital X of omega, the signal x, and the multiplication, which gets translated in frequency, as you know, in a convolution divided by 2 pi. Remember this coefficient 2 pi when the multiplication in frequency goes into the convolution, multiplication in time goes into convolution in frequency. So 1 divided by 2 pi, the Fourier transform of the train of deltas. Okay, so remember which is the Fourier transform of a train of deltas. The Fourier transform was another train of deltas, but the amplitude, it was 2 pi divided by t1, and the train of deltas was in frequency, and the separation was 2 pi divided by t1. This was the Fourier transform. So if we did do that, the 2 pi will go away with this 2 pi over here, and we will get 1 divided by t1, capital X convolve with the train of deltas. We can use the same dummy index, but the train of deltas are separated 2 pi divided by t1. So here we are faced with a convolution of a signal with a train of deltas. Remember that when we convolve a signal with a delta, the result is moving just the signal where the delta was. So this will translate into, we apply also the distributive property of the convolution with respect to the addition. So this will transform in the x signal displace or move where the delta were, or where the deltas were. Okay, so that's it. So let's draw this, and we will see something interesting here. If we draw x1 of omega, what we need to do is to draw the different x displays at the different points. So here we are going to draw x1 of omega. So for k equal to 0, this will give me the signal x around 0. Signal x, remember, that was that one. So we will have signal x over here. Okay, so it's amplitude 1 and going up to 1. This will be the case for k equal to 0. The next term, for example, k equal to 1, is this is divided by t1. So this is 1 divided by t1. Okay, because we have this factor over here. Okay, so now the next one, for k equal to 1, we need to move x to 2 pi divided by t1. But omega 1 was exactly 2 pi divided by t1. So this means that the next triangle, we need to move it over here, right over here. So this will be the corresponding triangle to index k equal to 1. And so on. To the left, it will happen the same. We'll have here minus 1 minus w1, and we will have over here the triangle to the left corresponding to k equal to minus 1. So what we are getting? What we are getting is a final result, which is a single signal which is constant all over the place, because adding together these triangles adds up to a single horizontal line of amplitude 1 divided by t1. So this train of triangles at the end gets into a constant signal, which is DC value, let's say, or a horizontal value of value 1 divided by T1. Okay, so we are done with x1. Let's go for x2. x2, if you can see over here, it's on the lower branch here. x2, let's put this here, x2 of omega, we are going to calculate. Okay, so x2 of t gets multiplied by this function, which is a train, another train of sets functions, separated also T1 apart. Okay, so let's see what do we have here. Let's try to picture this train of sets. We are now working in time. So set of t is shown over here. So set of t, if you draw set of t, it's just a triangle. It's a triangle of duration tau, sorry, it's a half duration tau and amplitude 1. This is what is defined in this equation. Okay, so here they tell me you have a train of set functions separated T1 apart. Okay, so for example, for k equal to 0, we will have here this triangle. Again, this what we are representing is this here. Okay, so for k equal to 0, we will have this, and this being tau. The next one will be displaced for k equal to 1, t to k equal to 1, t capital T units to the right. But look, tau, it's exactly the same, look at this, as capital T1. So we also have in this situation that the next triangle will be right over here. And the one on the left will be another triangle that will be over here, which translates in a signal. The train of set functions will also be a constant signal in a frequency. It will, and in this case of value 1. So this signal, I didn't do the right, this is x of omega, okay, and this is x2 of t. Okay, so in this case, this is a constant 1, so means that x2 of omega is exactly the same as x of t. Okay, so in other words, x2 of omega, it's exactly the same as x of omega, which was this triangle function. Okay, that's what we have in x2. Okay, let's move forward. Let's go again to the upper branch and calculate x3. x3 is just x1 passing through this pi filter. It's a filter, low pass filter with a width or half width to W1. So let's go and calculate that, x3. So x3 of omega, let's go for that. So x3 of omega, as I said, is just passing the signal at the input, which is x1 of omega, through the filter. So multiply through h1 of omega. Remember what we have seen before, that x1 of omega is a constant signal of value 1 divided by t1. This is what we got over here. So this will be 1 divided by t1 h1 of omega. So if we draw this, it's just taken the same signal h1 of omega, which was a pi of width to W1, sorry, with positive bandwidth, let's say 2W, and instead of being 1, this is now 1 divided by T1. Okay, this is 3 of omega. Okay, easy. Let's move forward. Now we go again to the lower branch, and we take function x2, and we also pass it through another low-pass filter, as you can see here. So let's calculate x4. Let's go for x4 of omega. So x4 of omega is just taking the input signal, which is x2 of omega, and multiplying that for the frequency response of the filter, which is h2 of omega. Okay, so what do we need to do? Let's write here both signals. We have signal x2 of omega. Let's write this here, x2 of omega. How did it look like? It was, remember, x2 of omega was x omega, which was a signal, a triangle signal. So we write here x2 of omega is like x of omega, and here the width was 2 pi divided by tau. Well, actually, it was W1, which is the same as 2 pi divided by T1. You will see now why do I put this frequency that way. Because if I write H2, H2 is another signal, it's a pi square, but it's much wider, because this goes all the way to 20 pi divided by tau. This is 10 times this point, it is 10 times away from the origin as this one. Okay, and the height of this H2 was 1. Okay, the height of X was also 1, by the way. So this triangle should be over here. Okay, should be over here. Okay, if we multiply the triangle by the square, the result is the triangle, because it's 0 outside of the triangle, and within the triangle it's multiplied by 1. So basically this is x2 of omega. This is what we get at the output of the system H1. Okay, let's keep moving forward. Finally, we need to add together x3 and x4 to form the signal y. Okay, so we go now to y, to calculate y of omega. So y of omega is just taking the two branches, the upper and lower branch, and adding them together. So it's x3 of omega plus x4 of omega. So let's remember what was each signal. x3 of omega was that one, and x4 of omega was x2. Okay, so if we add this square with this triangle, the result is this signal that you will see over here. So we have the square. The square will be this. Which was, this is x3. Okay, we'll go all the way to 2w1, and the height is 1 divided by t1. And we add here x2. x2 was a triangle that was over here, remember? So when we add both things together, then what we get is the triangle right on the top. Okay, so let's erase this. Let's erase this. We can erase this, and we can erase this. And this is the signal. The height here, as the x2 was height 1, this will be 1 plus 1 divided by t1. This is y of omega. Which are these positions here? This is omega 1, or 2 pi divided by 2. This is the y signal. Okay, so we are done. We calculated the output of the system to the signal x of t. Let's go now for the second part of the exercise, which is very straightforward, as you will see, because they ask us to calculate y of t. Y of t is the inverse Fourier transform of y of omega, and it is the inverse Fourier transform of x3 plus x4. So this will be the inverse Fourier transform of x3 plus the inverse Fourier transform of x4. Okay, so let's go step by step. Let's go first with x3. x3, we need to calculate the inverse Fourier transform of x3. If you go back to what x3 was, so this is the inverse Fourier transform of a pi of amplitude t1, center in the origin, and total width for omega 1. Total width. This is what x3 was. Okay? And again, here we have a Fourier transform that we have done in the past. In the past, this is somehow like the triangle thing. We have a pi in the frequency, and this will translate in a sync in time. We have done that in the past. Remember that we calculated the inverse Fourier transform of a pi omega divided by tau, and this inverse Fourier transform was 1 divided by 2 pi a tau sync of tau t divided by 2 pi. This was calculated in another exercise. Okay, so if we apply this into this case, we will get 4 divided by t1 square sync of 4 divided by t1 t. This is the inverse Fourier transform of x3. Let's go now for the inverse Fourier transform of x4. Okay, so this is the inverse Fourier transform. If you recall from above, x4 was a triangle in a frequency of half the duration omega 1. Again, we have a triangle in frequency that goes into a square sync in time. Remember, we calculated this, the inverse Fourier transform of a triangle of half width tau mediu, tau divided by 2, and amplitude 1 was 1 divided by 2 pi a, the amplitude, tau divided by 2, which is half the width, sync square of half width times t divided by 2 pi. If we apply this pair of transforms that were calculated in one exercise before, what you get is this is 1 divided by t1 sync square of t divided by t1. We have x4. So finally, y of t will be x3 plus x4, so 4 divided by t1 square, sync of 4 divided by t1t, plus 1 divided by t1, sync square of t divided by t1. Done. As you can see, this is it's not a difficult exercise, I think. It's just a matter of going step by step through each of the branches, applying what we already know from previous exercises, like transforming a train of deltas in time to a train of deltas in frequency, like the convolution with a train of deltas, and the Fourier transform between the triangle and the square, either in frequency or in time. Thank you for your attention, and see you in the next video. Bye bye.